Hello everybody, you are welcome to the presentation about the application of genetic algorithm with multi-objective optimization and control of two parallel inverter based microgrid. I am Asma Al-Farjani and the co-authors are Saeed Al-Aish, Ashraf Khalil and Awad Al-Shamah. This presentation is for the International Renewable Energy Congress 2020. The control coordination in distributed generators where the plug and play technique is normally implemented necessitates a systematic tuning methodology. Because the conventional tuning techniques comes at a cost of time consumption, so a multi-objective function-based genetic algorithm is formulated to search for the optimum values of the BI controller parameters that can restrain the system to confirm the stability with high performance. I will introduce the basic concept of our study, then the model of two parallel voltage source inverter, also the distributed control structure, and the basic concept of genetic algorithm optimization method. Finally, I will introduce the simulation results and conclusion. The microgrid typically composes three parts: renewable energy sources, power electronic circuits for control tasks, and loads. The main issue of this study is to optimize the controller gains of the proportional and integral control law for a two parallel inverter system using multi-objective genetic algorithm. This is the typical model of the two parallel voltage source inverter, where VDC1 and VDC2 are the input voltage of the two parallel inverter that is supplied from renewable energy sources. The suggested distributed control is designed such that the first inverter is controlled with a voltage control mode with two control loops, where the BI algorithm is used in both control loops as shown in figure 2. The inner control loops of the first inverter mainly regulate the output current with duty cycle signals. The output loop works as a voltage control loop, which restrains the output voltage and generates the DQ axis current references for the current loop. Therefore, the output of the outer voltage controller is considered as an input of the inner control loop. The second inverter is restrained with a power control mode. It is governed with two control loops in which the BI control law is superimposed in the inner control loop, and the proportional controller is implemented as the outer control loop, as shown in the figure 3. The space vector pulse width modulation is utilized to derive the sequence pulses. The power control mode is applied for the second inverter in that the output current components ID reference and IQ reference are utilized to control the output active and reactive power respectively. The genetic algorithm is an optimization technique. The objective function is a key element in the optimization of the genetic algorithm. The idea is that the objective function is developed to be dependent upon the controller parameters, and they are varied to optimize the fitness function. The objective function can be built to be elevated according to a single task, or it might consist of multi-tasks that are considered simultaneously in the optimization routines. In this work, the optimization of the controller parameters is carried out according to the criterion of minimizing of integral of square error. The implemented objective function is developed as a multi-objective function genetic algorithm with the integral square error criteria. This objective function is constructed such that the voltage error of the DQ components should be minimized. It consists of two sub-objective functions, as shown in these two equations. One for minimizing the sum of the direct error signal ED, and the second is to minimize the sum of the quadrature error signal EQ. It is important to note that the controller parameters are evaluated within the constraints or limits that are demonstrated in the following table. The final evaluated control input signals of the control loops for both inverters with multi-objective genetic algorithm, integral square error, and conventional techniques are presented in the following table. The genetic algorithm is basically implemented to discover the controller parameters that should maintain the system stability as well as to push the system to be at the optimum or nearly optimum mode of operation. The Pareto optimal front represents the best possible set of solutions combined between the two conflicting targets. Figure 4 shows that the trade-off between the two sub-objective functions ED and EQ. From the figure, the Pareto front obviously provides non-inferior solution points because an improvement in one sub-objective function ED requires degradation in the second one EQ. All the closed loop poles for both techniques are asymptotically stable. Therefore, one can conclude that the two algorithms are able to preserve the system stability. However, the multi-objective genetic algorithm integral square error provides better bandwidth than it is competitive. The peak value of the obtained waveforms is 170 volts, and clearly from figure 5 there is no significant oscillation has been recorded. Figure 6 shows that the balancing current has been achieved with good current sharing. The three-phase load current of 80 ampere is delivered by each inverter. The power sharing is verified according to the following scenario. Initially, the active and reactive power of the second inverter are specified at 10 kW and 2 kVAr respectively. After 0.05 seconds, these values are then reduced to 50%. The conclusion. In this paper, the genetic algorithm with multi-objective optimization based on integral square error criterion has been developed and implemented as an advanced and systematic controller tuning methodology for the two parallel inverter based microgrid. Stability analysis based on the linearized model of the considered system is also illustrated to confirm the advantage of the suggested technique over the conventional one. The obtained results reveal that with multi-objective genetic algorithm integral square error, the two parallel inverter can provide the desired waveforms with no significant distortion. In addition, very good power sharing can be achieved. The conventional tuning techniques, which are normally adapted according to the trial and error approach, might do the required task with a satisfactory performance. However, this usually comes at the cost of time consumption. Particularly with high-order systems, the controller tuning becomes too complicated and the expected performance cannot be guaranteed. Thank you for listening.